Okay, welcome all. I'm going to discuss heat exchanger experiment, calculation, and everything. So, what we have in heat exchanger? Tubular heats, right? So, tubular means tubes. So, we have two concentric tubes, right? So, this is inner, and we have hot water going through the inner tube. Hot water. So, in the outer tube, this we have cold water, right? In the outer tubes we have cold water. So cold cold in cold out. Okay, hot in hot out. So temperature, then we can have co-current and counter current. This one you know, right? So what we need to do in these calculations, like we have, like one thing is overall efficiency. Overall efficiency is basically about insulation. How good is the insulation of the heat exchanger? So hot water will emit the heat. It will give the heat to the cold, right? So Q emitted, right? So we are saying Q emitted is mass flow rate of hot times Cp of hot. So T hot out minus T hot in. So this is the heat emitted by the hot, and this should, and then the cold will absorb, isn't it? So cold will absorb. So it is m dot c, mass flow rate of cold CPC, and TC, uh, TC out minus TC cold in. Okay. Now here I had a mistake because temperature of the hot water will decrease, right? Temperature of hot water will decrease. So TC in minus out, in minus out. So this is the Q emitted, this is the Q absorbed. In ideal scenario, you may not have 100% insulation. For 100% insulation, emitted should be equal to absorbed. So we equate them, okay, or we can find the overall efficiency, which is QA over QE, okay, and in term of percentage, it is times 100. So if the absorb is more, it means that the cold water is getting some heat from outside as well, okay, and in opposite. So Q absorbed by Q emitted, right? So main job for us is to find overall heat transfer coefficients. Others are like temperature efficiency and these things, which is like very clear. The equations are given, right? So temperature efficiency, these thing you can calculate and just comment in the report. Okay. Main is to find the overall heat transfer coefficient U. Okay. So now, a few things you should know, like when the flow area, so we can have what, flow rate, right? So flow rate, if it is a volumetric flow rate, then we get the mass flow rate. Mass flow rate how is volumetric flow rate? If suppose is Q, then you multiply with the density, right? And if it is like the area of cross section is circular, right? So area of cross section is pi r square. So if we have like you should know, you know that velocity is q over a, right? So if you know the velocity, you can find the flow rate, right? Flow rate is v how much? The area of the flow for the hot is this pi r square. For the cold, what is the area of the flow? We have, if you see this view, this is inner and this is outer, right? So we have this in this area, cold flow rate, cold water is flowing, right? So if this is di, inner diameter is di, and this one is do, was the area pi by 4, inner out, outer radius minus inner, right? So pi by 4, area of this is this, minus area of the inner. Okay, so this is the area. Why we unit? Because if flow rate is given, or so you can know the velocity, and you can, from velocity you can get the flow rate and mass, flow rate and so on. Okay, so now let's see how we can find the overall heat transfer coefficient. Of overall heat transfer coefficient, Q, we said E, okay, U overall area, and then delta T LMTD, LMTD. So you know how to calculate LMTD, right? So area is area, where is the heat transfer going? In this, right? So inner diameter of the inner tube, okay, inner diameter of the inner tube. Then this is L, okay, pi dl. So area is pi, a small diameter, dl. Okay, L, I think in Excel some of you use. If you see the manual, it is a little bit confusing. It's not your fault, but I looked at the number. The value of U looks very high. Why? Because L, effective tube length. See, we had, if you remember in the lab, we have this and this. So each length is 360. So total length is basically 2 times 360. So please correct this one. Okay. So total length will be 0.72 meter. Okay. So this is what we have. Okay, let's go to the Excel right away and see here. We have flow rate, tau hot in minus tau hot out, to temperature. Okay, temperature cold in minus temperature cold out. Okay, so mass, this is the flow rate, uh, meter cube per second. Okay, I can make it kg per second. So what we need to do, we need to multiply with the density of water. Okay, let's say 1000. So this is density of water. Now it becomes mass flow rate. Okay, what we need to do, we need to find Q emitted, we need to find Q absorbed. Okay, um, okay, Q emitted is what? Mass flow rate of hot times Cp. Okay, Cp, it is 4.2 kilojoule. Okay, kilojoule per second per meter, and then mcp, right? And then emitted, hot in minus hot out. So this is Q absorbed in term of kilojoule. So just we can have in joule. So let's multiply by the 1000. This is the Q emitted. Okay, easy. Q absorbed, again mass flow rate of cold. Okay, so now we have here also flow rate. You can say mass flow rate. This is also mass flow rate. Okay, and then this is kilogram per second. So what we need to do, we need to multiply with this density of water. So Q absorbed is mass flow rate of this times Cp. We will assume same. Okay, Cp of cold and hot. There could be a little bit of difference. but let's assume same. So T cold out minus T cold in, right? So cold out is more than cold in, of course. So this is again now times 100. So a little bit, it's not 100% same, right? Uh, Not 100, sorry, 1000, right? In Joule. So our overall efficiency, this is this, right? Okay. So when we have very high temperature, high mass flow, this one is going down. Q absorb. Okay. So I will believe it in this data. Uh, Now what we need, Q emitted Q. So we will try to find. We need to find overall heat exchanger, right? Overall heat transfer coefficient. Area area is pi area of heat transfer pi times L. So now this times 2. Okay, pi d L, and d, which d, inner diameter, inner. So you can see I'm getting double area. So this is area. Now what we need to do, the LMTD, LMTD. So before LMTD we can find delta T1, delta T1, delta T2. Okay, this data for counter current. Okay, so counter current, what we have at one end, hot in minus cold out, hot in minus cold out, right? So if you have counter current, hot is going in this and then cold is coming in this. So TCI minus TCO, and this is THI. So this is hot and cold difference, and then we will have T hot out. Okay, so T hot in minus T cold out. This is delta T1. We can drag this one so you can see. Okay, delta T2 is another end. So T hot out minus T cold in. Okay. Now LMTD is delta T1 minus delta T2 divided by Ln delta T1 divided by delta T2. Okay. Okay, 1 minute. I have, I think, extra. Sorry. Ln T1 again, delta T1 minus delta T2 divided by Ln of what? Ln of delta T1 divided by delta T2. Okay, so this is the one. So this is the LNPT. Now you can see I need to report in up to significant digits. So Up to 2 is okay. Even up to 1 is fine. So this is LMTD. So area we know. Okay. So we can find the overall heat transfer coefficient easy. Um, so Q emitted divided by area and divided by LMTD. That's it, right? Yeah. So it is 1000 something. Okay. And sorry, area is constant, right? So I need to use dollar. And okay. So overall heat transfer coefficient is increasing when we increase the mass transfer mass flow rate of hot. Yeah, it makes sense, right? So if we increase the u and m dot h. So m dot h, if we increase m dot h, the q will be qe will be more, right? M dot h, sorry, cp cph and delta t, right? T hot. So when we increase this, QE heat transfer will be more. So the overall heat transfer coefficient will be more. Okay. So again, QE is U, area is pi, inner diameter dl LMTD, right? Okay, so that's it. I think stop here.